Hi everyone. Thank you for joining, and we're back for part two of the OPC FX series, and excited to sort of go deeper into this topic. And again, today I have with me Chhatrapati, and we'll be talking about implementing OPC UA FX into machines and into more details of how this can come about and yeah, as you remember, I think in the previous session, it was all about more or less the understanding the key aspects of OPC UFX, the benefits, the advantages, and the current state, right? And that basically was to set the tone to in terms of getting into a little more detail as we move forward with the subsequent sessions. So so again, just a background to this whole initiative. This is a webinar series that we're doing in collaboration with BNR Automation as well as Schneider Electric, and the objective is to sort of spread the word with of OPC UAFX and how the whole implementation can come about, and at the same time uh, have more OEMs and industrial machine builder OEMs as well as automation OEMs to collaborate and grow this sort of initiative and improve the adaptation of OPC UFX. So so I think I'll not take too much time to sort of go through the basics of it. So we'll get into the details. So this session again will run for about 45 minutes, and we'll have time for a Q&A. So feel free to drop in any questions you may have in the comment section, and we'll try to sort of address them then and there. And yeah, so in terms of I think just a quick recap in terms of where what we went through in the previous session a couple of weeks ago. So we basically spoke about uh, what the future of industrial automation technology look like, and in terms of where OPC UAFX fits in, and the different advantages and benefits that it could sort of offer to the discrete automation industry itself. Right? And of course, uh, with realizing those benefits, of course, there are some key considerations that we'll have to take into consideration. And that's when we went about highlighting different cases in terms of brownfield and greenfield in use cases, right? So um, we'll leave a link to the previous session, and if you have a chance, please do go through that, and I'm sure that'll set the tone to what we want to talk about in a little more detail today. So I think before we get into the details of how do you go about the embark on the journey of OPCUFX implementation into machines, uh, I think let's understand a little more on the different, I would say, aspects of OPCUFX and how this particular breakdown of different things came about, and sort of go from there. So I think over to you, Chhatrapati, if you can give us some details on that.
Yeah, sure, Nathan. So, OPCI FX is basically uh, extensions to existing core OPCA specification. So, these extensions help in adapting OPCA into the lower levels where different communication models can be achieved in terms of machine to machine communications and controller to compute or between controllers and even to the lower level where a controller can speak to devices as well. To achieve this, there are several aspects, and with respect to each of these aspects, the extensions have been defined, and some extensions are still it's a work in progress where different extensions are being expanded further. So there are several key extensions in the area of information model. Different information models have been defined to have this field level data exchange between different assets. Uh, and the communication model has been defined on how these communication establishment, monitoring of the communication, and maintaining it, and so on, and different network services as well, such as discovering the topology or identifying the assets on the network, and using time synchronization mechanisms to have more deterministic data exchange, and so on. And to have deterministic communication, TSN has been adopted. So it has been there on the IT and other network applications, and adopting TSN for the OPC AFX communications has enabled the applications to have deterministic, uh, time bound, and time bound data exchange, and this allows all the time critical applications like motion control and so on. And security. So OPCA itself has a very uh, strong security features already built in, and OPCA FX provides extensions on how this security infrastructure can be extended into field level and uh, other network communications that are a part of the OPCA FX. So basically, it allows all the basic features of encryption, authentication, data integrity, and protection against any other cyber threats that are out there. And most importantly, the OPCA security itself is a continuous evolving aspect of it. This is again based on in generic cyber security, whatever the improvements that are happening. Based on that, the adaptation is a continuous improvement that happens to OPCA security, and the same has been extended to OPCA FX as well. And interoperability is a very strong feature. So this ensures cross-vendor interoperability, so that controllers and devices from multiple vendors can coexist in the same system and talk to each other seamlessly. So a lot of early adopters or OPC AFX are doing rigorous interoperability testing with by attending different plug fests and other events. They are building prototypes and demos where devices and implementations from multiple vendors are being integrated and showcased as well. Then controller profile. This is again specific to controllers. So there is a reason why controllers are chosen to be the initial prototypes and development for OPC AFX. So the profile have been already defined for controllers, and other extensions are being defined, and other profiles are being worked on related to motion control, different instrumentations, IOs, and so on. So with all these extensions, OPC AFX is really set for having a complete end-to-end communication based on rich information models from sensor to cloud method. And as part of this, there is um, uh, there's a communication model that has been defined as part of the OPCA extension. And as you can see here, there are different possibilities, and each possibility brings out or addresses several different uh, new age use cases that are required to be addressed. So, for example, when you look at controller to compute, different dashboards, asset performance monitoring applications, predictive maintenance applications, different uh, uh, performance monitoring and optimization related applications, energy aware or energy conscious applications, and emission predictions. These type of use cases uh, becomes possible with controller to compute communication model, and running any sort of AI based algorithms and applications on the data that is available at a compute platform becomes easy, because the information model, the entire context of the data is preserved throughout the transition and communication. There is no mapping, or there's no protocol adapter, or there's no filtering or processing of the data that happens. And when you look at controller to controller, uh, again, this enables a lot of use cases in the machining industry. So where uh, these machines are being built for specific application by different machine builders who have their own strong area based on different applications. So they're being custom built with components from different vendors supporting different data models and different communication protocols and different even physical layers to connect and so on. So having an interoperable communication between machine to enable a much intelligent production line where the supervisory controls doesn't have to worry about each and everything opens up a lot of possibilities in terms of efficiency, interoperability, and so on. So this enables a lot of use cases for machines and other subsystems integration. And then controller to device, these are very normal use cases: IO data exchange, safety data, motion control. Um, Everything happens here. This is normal scenarios that are already have been there. But that is again now possible with OPC UA FX. And then compute to compute. This is again when you have different compute platforms running different applications with their own way of communicating and different types of messaging structures and data models. It becomes really difficult to exchange information between multiple compute applications. So, with OPC AFX adaptation, that becomes very much seamless and interoperable as well. Device to compute cases.
Yeah, I think we're just having some technical issues, so just bear with us, please.
Is where so the cases the controller include different diagnostics, condition monitoring, or sharing the audit logs, and any other smart instruments collecting condition monitoring parameters and sharing with the compute platform directly. And then the last one is device to device communication. There are very some cases where having information exchange between devices, where devices can do a localized action which doesn't depend on the controller input or intervention. So this enables possibility for such applications and use cases as well, I think.
Great. So I think uh, we pretty much saw the different possibilities and the key sort of extensions from the standard OPC UA spec, right? In terms of what entails OPC UA FX. I think before we sort of discuss or understand in terms of how it is implemented into machines finally, right? I think it'll be good to give understand a full picture of a typical machine and where it stands, and then sort of go into a little more detail. So if you can help us look at the bigger picture and then break it down, that would be great.
Yeah, sure. So yeah, we are just looking at a typical machine architecture, and then the components that it has, and these components are the specific machine architecture. When you map it to any example like a packing machine or something, then you get a little more meaning or understanding out of what each of these component is there for, and what it does. So these are typically the different components that are part of a machine. Maybe we can take an example of a packing machine. So power distribution handles the necessary power supply to all the components that are there, to the controller, to the drives and other actuators, conveyor belts, and so on. Uh, and then the controllers, they are the brains of the operation for the machine. They have the entire programming done so that they send specific commands to the actuators and keep reading the sensor data, and then any commands that are sent from HMI and other supervisory control are processed and executed by the controller. Then the actuators, they are the ones which do the actual physical movement. So they typically include different drives, motors, some hydraulic cylinders, or pneumatic devices, and so on. So in a packing machine, a motor moving a conveyor belt, or a hand which closes a box, or a suction grip which places a cap on a bottle, and so on, part of the actuator driven actions. And then there are sensors. They typically provide all the necessary contextual information to the controller. Different sensors like proximity sensor, temperature sensor, positioning sensor, and so on. So they can determine whether a specific product is placed on the belt, or in what position it is placed, what is the weight of the material that is being filled in, and so on. So this sensor data is sent to the controller, and controller makes necessary adjustments by sending specific commands to actuators, so that the overall packing process happens. HMIs are where uh, the commands are given by the operators. So it allows to start the machine, stop the machine, and make some adjustments to the setting, or monitor how the overall machine is performing, and so on. So and then communication system. This is where all the different sensors and actuators talking to the controller, HMI talking to the controller, and then any other supervisory controllers are uh, talking to the controller of this machine, and so on. So this is where uh, most of the today's discussion is going to be. It's part of the communication systems and related aspects is where we are going to look at in more detail. And of course, these machines have safety systems. So, depending on specific application, there can be stop buttons and other safety controllers and so on for safety systems. And end effectors is where you will see the final outcome of all these coming together, such as a arm placing a specific product in a specific position, or a specific hand closing a box, or another roller sealing the box, or a specific heat-based cutter cutting and sealing a packing roll and so on, you will see as the end effectors. So all these components talking to each other, and controller being aware of, and controlling the actuators, and responding to sensor data, all makes it work together as a machine.
Great. I think when no, thanks for breaking that down. So in terms of let's say uh, just to sort of understand some of the things that you've highlighted here, right? Like in terms of the data flow and the typical scenarios of how these different aspects come together for a specific use case. I think if you can briefly
Yeah,
touch on this, that would be helpful.
yeah. So we have looked at all the different components of a machine, and uh, basically what do they do. And then the main and important aspect of this machine is the communication requirements, and how uh, all these different components talk to each other. What are the different data flows that are there, uh, and in which scenario these data flows occurs. So with this, you'll get a complete overview of what a, like in a very generic sense, you'll understand what a machine is and how it performs. So sensor data flow, this is where sensors collect data on either product presence or position, weight, dimensions, and so on. And then this data is sent to the controller for processing. This is how controller understands what's going on the machine. And then controller itself, again, when it receives this input data, it makes decisions on pre-programmed logic, um, and based on that, it generates commands that needs to be sent to the actuators to perform specific tasks, such as moving a product, or sealing a package, and so on. And there is also this feedback data flow, where sensors continuously monitor the status of the machine and the products. And based on this feedback data flow, the controller makes necessary adjustments and corrections on real time, so that it allows a little bit threshold of movements and errors here and there to have a dynamic adjustment, and to make sure that the machine performs seamlessly. And then the HMI data flow, this is basically um, HMI receives data from the PLC, and in some cases from sensors as well. It displays that data for the operators. So typical use cases would include like showing some production rates, or any error messages or alerts that are raised by the rest of the components on the machine. or any maintenance alerts. So all these can show up, and then the operator can address those. And the data logging and analysis flow. This is where different data logs, including production counts or any downtime events or some error logs, they are all captured, and this data is stored and passed on to analyze, so that any trends can be identified, and based on that data any optimizations of performance can be done, or for any needs to do a predictive maintenance related analysis, and so on. So this is all of this is happening within a machine, um, but when there are multiple machines to perform a specific assembling or specific activities on a product in stages, there is a need for these machines to communicate with each other as well. So the machine to machine data flow usually covers some very good use cases. Like, for example, one is automated quality control. So if there is a machine which is only responsible for checking the quality of the products that are coming out, it can give real-time feedback to the producing machine or the packing machine based on the kind of issues that it is detecting, and it can be used again as part of the dynamic adjustment or real-time adjustment that is possible within the threshold of what a controller can do of the producing machine. And it can also, another use case is kind of energy optimization. So where depending on the current state of the previous machine and this machine, and at what rate the production is happening on the previous machine, some adjustments can be done to optimize the overall energy consumption. So like this, there are several use cases that would come into picture. So again, when you look at these data flows for sensor data flow, detect, detecting a product, and then for the controller to data flow, it is mainly processing and sending a command, and then for the actuator, it is taking an action like sealing a specific box, the movement which is responsible for sealing a box. And feedback is based on sensor at sealing station confirming that okay, the position is good and it has been sealed, and then if not, based on that, making an adjustments to improve it, and so on. And then the monitoring, where HMI keeps getting the data with which it can show some alerts and production information and so on to the operator. So I think with these two aspects, there is the different components and the kind of data flows that happens between the components, and what kind of scenarios these data flows covers. So with this, we get a high-level overview of a machine and how multiple machines on a production line can depend on and talk to each other.
Great, perfect. So I think now that we know the different aspects of how these the scenarios or the use cases and the data flows in a typical machine between these blocks, right, that you mentioned, I think it's the right time to sort of get into the crux of what we wanted to sort of talk today, right, in terms of what it takes to sort of transition towards OPC UA FX. What do machine OEMs have to consider? What does that journey look like? So I think if you can give us a little more of a breakdown into how that sort of transition happens, and then we can understand the details of that. Yeah.
Yeah, yeah, sure. So at least based on some example scenarios. I'm trying to generalize this. So it may not be exactly this approach for every case. So it depends on the composition of the current machine that you are looking at, where you are trying to adopt OPCA FX, and it also depends whether you are a machine builder who are trying to adopt OPCA FX, or you are an OEM who wants to a, produce components so that machine builders can adopt OPCA FX. So from that perspective, some of these are applicable to you, some of these are not applicable to you. So that judgment I would request the audience to make. But at a high level, this is what it looks like. So imagine a machine in its current state where um, different components and controllers are used, and with different types of physical layers, and then different communication protocols, different data models, and so on. And step by step, when we look at it, the first step would be to have a standard Ethernet as the physical layer, and then having OPCA enabled for the communication. And of course, that these two steps only provide interoperability to a certain degree, and then going further, picking and choosing and implementing the right information model based on your application specific use cases, and then expanding that to OPCA FX, uh, and then on top of it, enabling TSN. So this is where OPCA FX can work in some cases for non-deterministic applications as well, and then when you want a full-fledged determinism with um, time-bound delivery of the messages, you can have it with TSN as the base network, on top of which you can have OPCA FX. So from these aspects, we'll just look at how that transition looks like. This is again uh, in going forward in the subsequent webinars, we will cover a little more deeper technically on if you are an OEM who is trying to implement OPCA FX as part of your offerings. Let's say starting with any controller, what are the approaches, what are the considerations that needs to be taken care, hardware considerations, platform considerations, different stacks that are available. How do you make the configuration available to your end users based on your existing configuration tools and infrastructure? So all of that in detail we'll try to cover in the subsequent um, webinars. But today we will look at little bit higher level on how this transition looks and what are the typical steps, more from a machine builder perspective.
Perfect. So I think so. Let's go deeper into those 5 or 6 steps that you mentioned, right? Like I think that'll uh, help us understand where this journey takes us, right? And if you can get into the nitty gritties of how that comes about, that would be helpful.
Yes. Here, when you look at two machines, right? So they both have in a sense, where you are talking about a machine, it is mostly to the main controller of this machine, which has a connection to the uh, rest of the plant in terms of connection to a SCADA system. If you look at from that perspective, there could be different types of physical layers here, and then there could be a different uh, communication protocols that are already available, supported by these machines to talk to the outside. And the data, whatever this machine is uh, making it available for the rest of the system, how the data is structured, it also varies depending on these specific communication protocol. So, if you want to achieve any level of coordination between these two machines, you need to design a very tightly coupled custom solution. So where based on this that specific register map, you are trying to map the variables into your application, and then similarly you are trying to do the same from the other machine, and you're trying to map, and based on that you are building the logic to do specific use cases where you can achieve some level of coordination between these two machines. So this we can see how this becomes very difficult even for a minute change, or if some modifications happens on the register map, or the configuration of the controller, or the settings of the machine, anything. It would put again, you need some engineering effort and some customization effort on the solution. Uh, so here again, your current machines can be in different stages. So based on the kind of hardware and the kind of support that it already has for OPC and so on. So we will look at it from step-by-step perspective. Assuming that you have a unified physical layer, which is in this case Ethernet, still all the rest of the limitations that I have described earlier are still going to be there. Um, different protocols, data models being different, and still it is a custom built solution. So uh, the only benefit that you would get out of it is the physical layer. You will have the standard Ethernet, so that you don't have to deal with multiple types of physical layer and corresponding connecting and networking components. Um, Now, if we go to the next step, where um, we have controllers where OPC is supported, right? So here again, it um, provides a standard way of connecting to a OPC server and then gather the data and all that. But still, the information model could be different on each of these machines, since these are custom built machine, and the machine builder may have used components from different OEMs, and they might have configured the information model differently for these machines, even including the basics of identifying a machine and its nameplate and so on to that level. So still some customization is required to understand both the information models, and to digest that information and provide some level of coordination. Um, but however, if you adapt to any of these standardized information models, as shown in the next slide, uh, then uh, uh, then application can easily understand. So there are several standardized information models are already there for machines, and even within the machining industry, there are several applications are there. So for each of these type of machine, the profiles and information models have been standardized. So for example, if you take a plastic and rubber machinery for extruders, so within within the extruder different types of components. So for the whole thing, there are several information models that have been defined. For packing machines, so there are information models that have been standardized with PackML and so on. So when you use an application specific standardized information model as a base for your implementation, then it becomes very easy to understand the information that is coming from these machines, even though they are custom built from different vendors, supporting different features. Still, uh, you'll be able to identify these machines, you'll be able to understand what to uh, ask when you need a specific information and so on. Uh, so with this, some degree of um, M2M coordination can be achieved in a better way compared to the previous implementations. Now, beyond this, instead of simple OPC with information modeling, if you are adopting a controller which has OPC UA FX built in, then you will be able to establish a direct communication between these two machines. So within the OPC FX, there is this uh, rich tools with which um, you can define or describe the device, and then you can configure different data sets, and then define connections to establish between these machines, exchanging these data sets. So the whole workflow is there with which you can establish a machine to machine communication. And here, different use cases which are not very high demanding in terms of time critical or time sensitivity can be achieved with this, still using the standard Ethernet. So connection managers can establish connections between these machine to machine, and any of these use cases like we talked about earlier, like an automated um, quality checking machine can give feedback to the producing machine, and a producing machine can make necessary adjustments. So all of this can happen without the rest of the system getting involved in these lower level coordinated activities. And if the requirements are beyond this, and the application demand is to have a complete deterministic and real time data exchange between these machines as well, then the Ethernet can be upgraded with support to the TSN based. So once you do that, uh, then you will have a completely deterministic uh, data exchange, like it is shown in the next slide. So here, yeah. So all the time critical and interoperable controller to controller applications can function directly, and any time critical machine to machine data exchanges also becomes possible here. Here we definitely need to talk a little more on adapting TSN. That itself comes with its own few of the challenges, where you may have to upgrade some of the networking components in terms of hardware, and then you need to be uh, or at least the staff need to be a little more trained on understanding how the TSN network works. And if you want to apply determinism for these specific communications, what kind of configurations you should do and push to these networking, TSN based networking components, and so on. So, from that aspects as well, as a lot of work is being done where automated tools are being developed, which can understand the current limitations of bandwidth, what is the network segmentation, what is the network topology looks like, and what kind of data packets with what cycle times needs to be exchanged between two specific nodes within the network. So understanding of all these data flows and their bandwidth requirements and the cycle time requirements, based on all this, determining the scheduling configurations, and then the uh, timing configurations, priority configurations, uh, determining these, and then being able to push these configurations onto the TSN supporting network components, so that the entire network is configured to prioritize these deterministic data flows, and rest of the data can coexist on the network without determinism. So with that, you will have complete OPC FX adapted machine to machine communication, anything. So going
Oh,
further, within a machine to achieve to the same level of determinism, again the network within the machine again has to adapt to TSN based networks, and then the devices as well should start supporting the OPC AFX on them. That's when even the controller to device and device to compute kind of scenarios as well uh, can be operating on the OPC FX based communications. But mm, being able to support machine to machine communication with a controller which supports OPC FX over TSN, that itself opens up a lot of additional business use cases, data driven services, and so on.
perfect. I think thanks for summing up that like six step from the initial state in terms of where it could be. Again, like you said, uh, different OEMs could be in different states. Like it could be uh, the starting position could be different, like in terms of where their current situation is. But at the same time, uh, all these different aspects are very critical towards arriving at a fully functional deterministic OPC UA FX implementation, right? So I think this is what we wanted to sort of arrive at in terms of understanding the
Yeah.
different aspects of
So
uh, uh, yeah. Go on.
even from the foundation and the technology standpoint as well, from the OPCFX technology standpoint as well, it is very clear that this will happen gradually and phase by phase. So there are several resources and several accommodations that are being done, being provided as part of the uh, technology specification and other aspects, which would accommodate for you to have these hybrid networks and hybrid infrastructures where components supporting OPC-AFX, components supporting TSN and OPC-AFX over TSN can coexist with rest of the systems and still work as a subsystem and then integrate to the rest of the systems, and so on. So uh, this actually makes it much easier to start the adaptation journey and do a gradual adaptation step by step.
Perfect. I think, yeah, thanks for summing up that, CP. I think uh, we've consolidated what we wanted to. I think and yeah, I think moving forward we'll be getting into a little more details, and I think so uh, so the following session is really getting into the networks itself, right? The network and the topology and how that comes together, from an OPC UFX standpoint. So I think we'll be doing this in a couple of weeks again, uh, uh, and before that, like if you have any questions specific to this, feel free to use the comment section, as well as the OPC UA FX professionals group that we have on LinkedIn as well. So anytime the respective subject matter experts can sort of address your queries and any questions you may have on that front. So happy to sort of keep it engaged and sort of address any points that you might have, right? And we'll continue to sort of um, share insightful information of where this technology stands today, and different aspects associated to the different gradual steps to going about this journey, and I'm sure those might be helpful for you whenever you sort of uh, look at this aspect. Um, so yeah, I think I'll conclude the session for today. And again, this webinar series is a collaboration with BNR Automation and Standard Electric, and we sort of encourage different OEMs to sort of uh, collaborate and contribute towards this initiative. And I think the more the merrier. And if anyone would like to sort of understand more, happy to sort of uh, get in touch and sort of go about this. So again, it was fantastic hearing from you, CP. I think thanks again, and
Thank
we hope to have another insightful session in a couple of weeks. And thank you everyone for taking time and being with us for about an hour. And we'll definitely see you soon in a couple of weeks. And any questions in between, feel free to drop it in, and we'll get back to you. Thanks again. Have a good weekend. Bye bye.
you. Thank you. Bye.